There are two extremely important chemical processes that you're going to hit many times throughout your chemistry career: oxidation and reduction. And we're going to have a first look at these two processes right now. Oxidation is defined as three ways. Originally, and this is where the name comes from, it's when a substance gains oxygen. For example, carbon gaining O2 to become CO2. Okay. Again, historically, sometimes it doesn't have to gain oxygen, but it loses hydrogen. Historically, back in the old days, oxygen and hydrogen, of course, both being the component parts of water, were very important and opposite sides of the same coin reactively. So, for example, something loses hydrogen when you get ethanol here going to something called ethanal or acetaldehyde. If you look at this, compare them, you've got the CH3, you've got a C, an O, this H and H, but we've lost that H2. So this is an example of something losing hydrogen. It is oxidized. Undoubtedly, however, where you have heard of oxidation before is a situation in which a substance loses one or more electrons, and of course we saw this extensively earlier in metals forming metal cations and losing that electron. Okay, so oxidation has any one of these three definitions. The first two are nice reactive macroscopic type of definitions. They're the ones that you will see when you get to organic chemistry a lot. Third one is a much more general one, and of course is the one that's interesting to us really right now. Now, oxidation is that, reduction is the opposite of oxidation. So reduction, and again this is where the name comes from, is where a substance is reduced in how much oxygen it's got. It loses oxygen. So for example, mercuric oxide going to mercury. Oxidation, where something loses hydrogen, so that's reduction, where something gains hydrogen. Here you can see CH2 ethene becoming CH3 ethane. And of course, if oxidation is losing electrons, reduction is where something gains electrons. For example, Cl2 gaining 2 electrons to become 2 chlorides. Now, we will be studying these processes together. It's not necessarily obvious to see that oxidation and reduction must occur together when you look at either of the first two definitions, but you can surely appreciate that if something is going to lose electrons, it has to lose them to something, so thus something else has to gain electrons. And of course, the same way, if something is going to gain electrons, it's got to gain them from somewhere, so something has to lose electrons. So we study reactions as a combination of oxidation and reduction, and we name them as that nice little contraction of those. We take reduction, we take oxidation, and bring the two starters together to redox. I actually don't particularly like this idea because for me, you got to lose something before something else can gain it, so it should be ox-red, but that doesn't flow nearly as nicely off the tongue. Again, I will make the point that if you're not watching this as a show, you totally missed the beautiful animation there that brought the red together with the ox. Now, we've seen ionic redox processes since we started looking at things, right? We talked about metal atoms losing electrons, thus we can now say they want to be oxidized. Talk about non-metal atoms wanting to gain electrons. Now we can say they want to be reduced. But we can use the idea of this ionic stuff and change to identify a reaction as being a redox reaction. For example, sodium plus chlorine makes sodium chloride. Let's have a closer look at that in terms now of examining it as oxidation and reduction rather than just the way we looked at it back in an earlier chapter. So sodium and chlorine, now I've split it up to Na plus and Cl minus, so we can identify things a little bit better. Let's look at the charges on these things. The sodium there is 0. Sodium plus has a charge of +1. So therefore, as we go from sodium to +1, the sodium has gone up in charge. It gets more positive. How does something get more positive? It loses an electron, thus the sodium has undergone oxidation. Same idea for the chlorine. The chlorine starts off with a 0 charge, it ends up with a -1 charge. So as we go from the left to the right, we see that the chlorine has gone down in charge, become more negative. To do that, the only way to do that is to gain electrons. Therefore, we say that the chlorine has undergone reduction. We can follow this process and use this process in order to help us balance the equations. Now, this is one that you're probably thinking, I don't need any help to balance this, but it's not a bad starting point. So again, this is where we are. We've got those charges there. Now, the first thing to see is that, of course, we have an imbalance in the chlorines. We got 2 chlorines on the left hand side, we only have 2 chlorines on the right hand side. So before we do anything, we got to make sure that we actually know how many atoms of a particular type are balanced before we even balance the main equation. So that means we've got to start off by sticking a little 2 in front of the Cl-. Okay? Now if we again link these up but do it in terms of the redox process, the sodium going to sodium plus, that is a 1 electron change. It's losing 1 electron as it does that. The Cl2 going to 2Cl-, however, that's 2 electrons, right? Each chlorine goes from 0 to -1, but we got 2 chlorines, so that's 2 electrons there. You have to have equal numbers of electrons lost and gained. You can't, as we said before, something can't lose electrons without something gaining them. Something cannot gain electrons without something else having lost them. So one of the important things we have to do when we are studying redox equations is to balance out the electrons. Now, how are we going to do that? Well, obviously we need 2 sodiums to be doing their losing 1 electron each to balance out the 2 chlorines gaining their electrons. So let's put in the 2's right there, and we can see that now we have 2 electrons to balance it out. Well, that might have seemed a little bit hard and painful almost of an explanation for something that was much easier than that. But I wanted you to appreciate how we use the ideas of reduction and oxidation, right? First of all, how we have to identify an oxidation and reduction, and then how we can use, or in fact we have to take into account the fact that you've got to balance your electrons as well as the atoms when we're balancing redox equations. And we can now use this for a much more complicated type system, and what I'm going to call generally non-ionic redox reactions. So we'll start off with, how do you identify a non-ionic redox reaction? Earlier on I said that oxidation is where ethanol becomes ethanal. Well, it's an oxidation because the ethanol loses 2 hydrogens. But how can we reconcile this with the much more general description that oxidation is where something loses electrons? There's no electrons there, there's no charge there. What on earth are we talking about? Well, what we have to do is, instead of using actual charges, we have to use fake charges, which means that we use a concept known as oxidation numbers. Oxidation numbers, oh, and I'm stuck in your head, they're either the charges on an atom, if we know that atom has a charge, like Na plus has an oxidation number of +1, or they are fake charges, where the atom doesn't have an express charge. We're just looking at it, oxidation numbers, as a way to kind of follow the reaction to see how it works as a redox reaction. Now, there's 2 ways in which one can define the oxidation number for an atom. Much later in this course, and then if you get to organic chemistry as well, you will define the oxidation number for every single atom in a molecule. But you do that by having a knowledge of the structure, a knowledge of what atoms are bonded to what. At this stage, we're just going to go through and we're going to assign the average oxidation numbers for a type of atom in a molecule. Okay, and to do that, we have to follow some rules. We got to start off by saying every type of atom in a species gets an oxidation number that, as I said, is going to be the average. The total oxidation number, when you add up all the oxidation numbers in a species, a molecule, an ion, whatever, has to equal the charge on that species, because of course the oxidation numbers are either the charges or the fake charges. Okay? And sometimes this is all you need. You should be able to just, for example, if I've got Na plus, what's the oxidation number? +1. If I have sodium, what's the oxidation number? 0. If I have Cl2, what's the oxidation number? 0. Okay? But most of the times, if you're dealing with compounds, you're not going to be able to have assigned the oxidation numbers by just doing these first two steps. And so you have to use your chemical knowledge, and that's a scary idea, isn't it? But in a very, very significant associated order. Okay? Okay, if you need to continue on to assign oxidation numbers in compounds, there's this certain list of rules, guidelines, as I said, associated with your chemistry knowledge. First thing you should know about are metal cations. Okay, if you've got a metal cation in a compound and you need to be able to recognize whether something is a metal cation, it's a cation, it's got a charge. So the oxidation number is just going to be the charge on that cation. So if you have a compound that's got sodium in it, potassium, lithium, it's an alkali metal cation. Alkali metals form cations with a charge of +1. If you have an alkaline earth metal in there, you know it's going to be a +2 cation, oxidation number +2. If you have aluminum or gallium in there as a cation, you know it makes a +3 cation, and so its oxidation number will be +3, and so on. So just using what you know about metal cations, if you've got a metal cation in a compound, you can immediately assign the oxidation number. Then going to non-metals. Well, the first non-metal of interest is fluorine. Fluorine is, as you're going to find out as we go through this course, for various reasons, an amazingly dominant atom. Fluorine is going to get an electron. It doesn't matter if that's a literal getting of an electron, as we've seen when it makes the fluoride anion, or if it's a figurative and a fake charge gaining of electron in a compound. You can always say, when you have a fluorine in a compound, whether it's a covalent compound or an ionic compound, fluorine is going to have an oxidation number of -1. The only time you see fluorine without -1 is when it is in elemental fluorine, F2. Well, in F2 the charge is 0, so the average oxidation number of the fluorines is 0. But that's the only time fluorine is not -1. Hydrogen, by virtue of the fact it only has one electron and it's somewhat of a silly atom, is also rather picky in which oxidation numbers it forms. It can have an oxidation number of 0, as in elemental hydrogen, because again, if the charge is 0 and all you have are 2 hydrogens, the average oxidation number of the hydrogen's got to be 0. Hydrogen can be -1 to be a hydride. It makes hydrides with certain metals. So if you have sodium hydride, well, you got sodium there. Got to be sodium +1, so therefore the hydrogen has to be -1 for the NaH to have a 0 overall charge. Failing that though, if you get to this stage and you've got hydrogens, you know that the oxidation number of hydrogen will be +1. Oxygen is also a kind of a nice one. Oxygen has more exceptions to this than either hydrogen or fluorine, but by and large, if you get to this stage in trying to work out what oxidation numbers are, you can be safe in assuming all of the oxygens are -2. You see, oxygen is 0 when it's with itself, right? In dioxygen, O2, or ozone, O3, we say the average oxidation number of the oxygen atom is 0. Oxygen can also be +2, for example, in OF2, right? The fluorine is -1, you got 2 fluorines, 2 times -1 is -2, so the oxygen has to be +2. Oxygen can be strange oxidation numbers when it's in peroxide anion or the superoxide anion, but there what it is dictated by the charge of the metal atom. And of course in something like hydrogen peroxide, for example, the hydrogen's got to be +1, so the oxygens have to be -1. But on that, you see oxygen is going to be -2. Now we could go on assigning these things, but as we go further and further and further down the list, we get to where there are more and more and more exceptions. So I prefer to stop right here and just allow us to think things through and assign intelligence and so on. If by the time you get to this stage, so you've made sure that you know that the total sum of the oxidation numbers is going to be equal to charge, you've taken care of any metal cations, you've taken care of any fluorines, hydrogens and oxygens in there. If you've still got some unassigned oxidation numbers, then the best practice is you say, okay, whatever the atom is closest to fluorine, I'm going to say that that makes the anion that it wants to. It might be a real anion, it might be a fake anion, and when you've done that, you should be able to take care of any unassigned atoms. We'll do an example of that in a minute because I know that it sounds a little bit weird. But anyway, let's do some examples generally. We'll start with ethanol, right? The one that started this discussion. How can we assign charges? How can we assign fake charges to something like ethanol? Well, the first thing we do is we rewrite it as C2H6O. We don't care that those hydrogens, what, 3 on one carbon, 2 on another carbon, 1 on a hydrogen. We would care if we were organic chemists and we were trying to assign individual oxidation numbers to individual atoms. But all we want is average oxidation numbers. So we've got 2 carbons, we've got 6 hydrogens, and we have an oxygen. So therefore we need an average oxidation number for carbon, an average number for hydrogen, and an average number for oxygen. First thing we do is we say, well, the total oxidation numbers gotta equal the charge. So we have 2 carbons, we have 6 hydrogens, we have an oxygen. And when we take that oxidation number for carbon times 2 plus the number for hydrogen times 6 plus the number for oxygen, that's got to be 0 because this is a neutral molecule. There's no charge up there. Okay. Now we can't just now say, all right, we know what they all are. We have to go through a little process. So as we go through that process, the first one we say is, do we have any metal cations? And the answer is no. Then we say, do we have any fluorine? And the answer is no. Then we say, do we have hydrogen? And say, yes. So the hydrogen is going to be +1. So let's pop that one in. And so now we have the 2 carbons, still don't know those, 6 times 1 for the hydrogens, and of course the oxygen also we still don't know. So we still can't assign all these atoms, so let's continue on. After hydrogen we get oxygen. If you've got any oxygen still, then the charge is -2. The oxidation number is -2. We'll pop that in. So 2 carbons plus 6 times 1 plus -2 is 0. I am making a meal of this. 2 carbons plus 6 minus 2 is 0. 2 carbons -4. Therefore, carbon in ethanol has an oxidation number, a fake charge of -2. Another one. K2CR2O7, potassium dichromate. Well, we're going to need oxidation numbers for the K, for the chromium, and for the oxygen. And then, of course, the total oxidation number has to equal the charge. Well, potassium chromate overall has no overall charge, right? So 0. And we got 2 potassiums, we got 2 chromiums, we have 7 oxygens in there. 3 unknowns, so now we have to move on with the next step. Well, the first deal, do we have an alkali metal? Yes, we have potassium. You see an alkali metal in a compound, its oxidation number is +1. So pop that in. 2 times +1, plus, still don't know the chromiums, still don't know the oxygens, so we still can't assign all the atoms. So continuing on down, do we have fluorine? No. Do we have hydrogen? No. Do we have oxygen? Yes, so the oxygen's going to be -2. Pop that in, we got 2 times +1 for the potassiums, 2 times the chromiums, 7 times -2 for the oxygens, got to add up to be 0. So +2 plus 2 to the chromiums minus 14 is 0. Therefore, 2 times the chromium is 12. Each chromium on average has an oxidation number of +6, the highest oxidation number possible for a chromium atom. One more example, and this is a sneaky, mean, nasty one. Consider cyanide, Cn-. So obviously we need oxidation numbers for the carbon, oxidation number for the nitrogen. Carbon plus the nitrogen has to be the charge. Now in this case, this is the first example where we actually see where we're looking at a polyatomic ion, so the charge isn't 0, the charge is -1. So we go through our steps then. We don't know carbon or nitrogen, so we say, do we have an alkali metal? No. Do we have generally a metal cation? No. Do we have fluorine? No. Do we have hydrogen? No. Do we have oxygen? No. We are totally out of luck. We might as well just jack this in, go off, become a history major, an English major, work at McDonald's, whatever you want. Well, this is where we need to use that extra little bit of chemical knowledge. Okay, we say nitrogen is closer to fluorine. What we'll see later on in the course is that this means that nitrogen is a more dominant atom. Nitrogen is going to get what it wants more often than not, compared to anything that's not closer to fluorine. Now we know from earlier that nitrogen is a pnictogen, group 5. Nitrogen's desire would be to make a -3 anion. So why don't we just say that that's what it is in this substance? Its fake charge is -3. Oxidation number -3. So now we just plug that in. Carbon plus -3 is -1. The carbon in cyanide is +2. Well, great, jolly good. Now we're world experts on oxidation numbers, but that was a long deviation from our original question, which is when we don't have clear, obvious charges, how do we identify a process as being an oxidation or a reduction in terms of losing or gaining electrons? We started off by using the ethanol to ethanal example. This is obviously an oxidation because we lose 2 hydrogen atoms. However, how do we explain that in terms of the electron loss that must be present for it to be an oxidation? Well, first of all, let's rearrange the structural formulas in a way that makes it easier to assign the average oxidation numbers. Going through our various lists, hydrogen's going to be +1 in both of these species. Oxygen's going to be -2 in both of these species. We of course did ethanol earlier in terms of assigning the oxidation number of the carbon, right? 2 carbons plus 6 hydrogens bias. The oxygen is going to be 0. Throw in the 1 and the -2 for the hydrogen and the oxygen respectively. Carbon is -2. Let's do the same process for the product for ethanol, the C2H4O. So we're getting 2 carbons plus now 4 hydrogens, 1 plus the oxygen, -2 is 0. Simple algebra, and we end up with the carbon is -1. So the carbon starts off as -2, ends up on average as -1. Well, it's gone up in oxidation number. It means it's gone up in fake charge. It's become more positive. How does something become more positive? It loses an electron. If it loses an electron, it is oxidized. Now we should now move on in this presentation to the next step, which if you remember is once we've identified something as being an oxidation or reduction, how can we use the change in electrons to help us balance redox equations? Well, this has already been a 23-minute presentation, so we'll leave this one and move on to the next.